Hello students, in this video we'll begin our discussion on graphs. So a graph, in the mathematical sense, is a collection of vertices, which we're going to write as V, V1, V2, Vn, and pairs of vertices that are unordered. We're going to talk about undirected graphs first, and a collection of edges, which we're going to write as E, and E is just a subset of unordered pairs of the vertices, a subcollection of all unordered pairs of vertices. The key feature here is that you need to have a pair of vertices. So an edge is a pair of vertices. So edges in a graph are pairs of vertices. An edge is a pair of vertices unordered. Later, we'll discuss ordered pairs of vertices, which will give us directed graphs. Okay? So that's a graph. Of course, we're saying this is undirected. Undirected. Great. And so let's just draw some graphs. So graphs can be very simple, they can be very complex. So here's an example of a simple graph. I have my V1 and I have my V2, and I'm just going to draw a line segment between V1 and V2. That is a graph over there. I have two vertices and one edge, right? So this over here is an edge, and those two things, V1 and V2, are my vertices. Okay? We can draw more complex graphs. Here's one of my favorite ones, just a triangle, right? That's a V1, that's a V2, and that's V3. That's a triangle, so I have three edges and three vertices over here. So this is three edges over here, three vertices in this example. So I have edge, 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 right? So three edges in that example. Let's do another example. So of course, it doesn't have to be these symmetric things over here too. It can be a little bit strange, right? I can do something like this. There's my V1, that can go to V2, that can go to V3, that can go to V4, that can go to V5, that can go to V6. And then we can have something funny that happens at V6. I can do something like this. I can make a loop, right? So this is a loop. And so what are loops? Loops are edges where the ordered pair is the same, right? It's a pair of vertices where the pair of vertices consists of the same vertex, right? These are pairs of vertices with the same vertex. Okay? And so loops can be fun. I can put lots of loops in these things. That's another example of a graph. But I'm very interested in the situation when I don't have sort of redundancies, right? So for example, I could have a situation where I had a subcollection of all unordered pairs. I could have V1 and V2 listed once. I could have V1 to V2 listed twice. Or I could have V1 to V2 listed 3 times or 4 times or 5 times. In other words, in my list of pairs, I could have V1 to V2 listed a whole bunch of different times, and there'd be a lot of redundancy. Once I tell you V1, V2 is in my set of edges, I don't need to say V1, V2 is an edge again, V1, V2 is an edge again. In certain cases where you might want to talk about weightings, you might want to do that. But in this very simple case, in the example of a simple graph, we're not going to have these multi-edges where I'm counting V1, V2 many times, or I have these loops in the situation. I just want to consider graphs that are undirected and don't have loops and don't have multi-edges. That's the situation we're going to be most interested in. And so now we want to develop up some more notation with these graphs over here. So let me draw one more sort of fun example, right? And these are going to come up a lot in our discussion over here. So I'm going to draw a pentagon over here. So there's going to be 5 vertices, V1, V2, V3, V4, and V5. They're my vertices of this graph over here. And I'm going to connect every vertex. So in other words, I'm just going to get every single possible combination. So V1 is going to go to V2, it's going to go to V3, going to go to V4, going to go to V5. V2 is going to go to what? V2 goes to V1 and V3, it's also going to go to V5, and it's also going to go to V4. And then what else can we have then? So that takes care of V2. So V2 goes to V1, V3, V4, V5. V3 is going to V2, it's going to V1, it's going to V4, and it's also going to go to V5 over here. So we have this over here. And now what do we see? We see that V5 goes to 1, 2, 3, 4. V1 goes to 2, 3, 4, 5. V3 goes to 4, 5, 1, 2. V4 goes to 5, 1, 2, 3. Every vertex connects with another vertex. This is an example of a complete graph. Complete graph. And this one over here is called K. They have special notations called K5, a complete graph. You get this beautiful picture over here too, right? And so I've sort of unintentionally hidden ideas of coloring these graphs. And so in further videos, we're going to discuss coloring of these graphs and see sort of the smallest number. In some sense, that will give us our discussion into Ramsey theory, which is really interesting and has lots of really cool mathematical properties. So that's an example of a graph too. And now what I want to talk about is this idea of degree of a vertex, right? And so this is in some sense the first and the most elementary example of a theorem in graph theory. So here's our theorem. And that says to define the degree of a vertex, this is called the degree, to be the number of edges which emanate from V. So if I looked at this V4 over here, and this first graph over here, there's one edge that emanates from it, there's another edge that emanates from it. So the degree of V4 over here, for example, would be equal to 2. If I look at this perfect graph over this complete graph over here, let's look at any of these vertices. If I look at this V2 over here, notice that the degree of V2 over here would be equal to what? There's one edge, two edge, three edge, four edge, so the degree of this would be equal to 4, okay? Over here, what's the degree of V2? The degree of V2 is equal to 2. Over here, the degree of V2 is equal to 1, right? Over here, the degree of V6, there's a loop, that's 1, and then going to V5, that's 2. Okay, so what does the degree theorem say? This is called the handshake theorem. So we should probably say this, it's typically called the handshake theorem. And broadly speaking, there's always two parties to a handshake. There's always two parties to a handshake. Okay? And so what does our theorem tell us? It says, here's the big result, it says, if I sum over all V a vertex, the degree of V, okay? If I sum all the degrees of every vertex in the graph, I get 2 times the number of edges. Which you can write as 2 absolute value mod E like that. And the proof, of course, is just the fact that there's two parties to a handshake, right? And so the proof of this is relatively straightforward, right? In the proof, we'll write it in just one line. Each edge is counted twice. There's our proof. Okay, let's actually try to understand that a little bit, right? So if I look at this edge over here, this edge is picked up by the degree of V3 and is picked up by the degree of V4. So this edge over here is counted once by the V3 degree and once by the V4 degree. If you look over here, in this complete graph over here, if I look at this edge over here is picked up from V1 and it's picked up from V2. So this edge over here is picked up once in the degree of V1 and once in the degree of V2. So each edge is counted twice, which means if I add up all the degrees, I just have the number of edges, but I have to count them twice, right? So I multiply the number of edges by 2, and that gives me an accurate count. While it's very elementary to prove this handshake lemma, it's actually very useful in characterizing when certain situations from graphs can occur, because we know that the sum of the degrees has to be even. So if there's a violation of parity, we can make conclusions about the sum of degrees and other factors like this. Thank you very much.